So in this lecture, we will learn about Bolzano Weierstrass Theorem. So let me share the screen. Topic is Bolzano Weierstrass Theorem for existence of limit point. Bolzano Weierstrass Theorem. So according to statement of Bolzano Weierstrass theorem, every infinite and bounded subset of R has a limit point. Every infinite and bounded subset. Every infinite and bounded subset of real numbers R has a limit point. Or in other words, we can say that if S is an infinite bounded subset of R, then its derived set will be non-empty. So in other words, I can say that if set is infinite, if set is an infinite and bounded subset of R, then its derived set will be non-empty. Then derived set will be non-empty. We know the derived set is collection of all limit points. So in that case, there exists at least one limit point. The derived set is non-empty means there exists at least one limit point. So here two important observation. Actually, this one is the necessary condition for existence of limit point. So if the set is infinite and bounded, then there is always guarantee for the existence of limit point of the set. Even we will see various examples that even if set is infinite and not bounded, then it may or may not have limit point. But for existence of limit point, this one is the necessary condition that if the given set is infinite and bounded. So before coming to this, let me recall some basic definitions which I have already discussed. I mean, what we mean by bounded set, what we mean by supremum and infimum of a set, what we mean by limit point. Actually, I'm going to explain this Bolzano Weierstrass theorem by two different methods. One using the method of this nested interval lemma. I will prove this using nested interval lemma, and another by different method using this definition of supremum or infimum. I'm going to provide you the proof of this Bolzano Weierstrass theorem. So let me first recall the definition which we required here. However, already I have discussed, but again I want to just recall those definitions. So in that, the first one is that what we mean by bounded set. So let me recall that what we mean by bounded set, what we mean by completeness property of real numbers. So we already know that if there exist real numbers small m and say capital M, or small k and capital K, whatever notation you are taking, if these are real numbers such that for every x belonging to the set, this m is less than equal to x is less than equal to capital M. This small m and capital M are real numbers. So if there exists real numbers such that every member of the set S is enclosed in this small m and capital M between these real numbers, small and capital M. This implies that S is bounded. This is set. The given set is bounded, and this capital M and small m are called an upper and lower bounds. And we know from ordered completeness property of R that whenever for a given set, I mean for a non-empty bounded set which is bounded above, for a non-empty bounded set, for a non-bounded, when we say that the set is bounded, means it is bounded above as well as bounded below. And in case if it is bounded above, then among all its upper bound, The least one is called a supremum, which we have already studied. So let me recall the definition. And similarly, in the case of all its lower bound, greatest among all the lower bound is called as infimum. So for existence of supremum and infimum, boundedness is required. If the given set is bounded above, then among all its upper bound, the least one is called as supremum. So boundedness is must for existence of supremum. That is, if the given set is bounded above, then there is guarantee of existence of supremum. So for this, what we will do, that let me write the definition of this, what we mean by supremum of a set. So supremum of a set. The least upper bound of the set say S subset of R. The least upper bound of the set is called supremum. That is, say supremum of the set is, if let me denote by this capital M by the supremum of the set. Here we are claiming, however, already I have taken this notation, but here I am claiming that suppose supremum of the set is capital this M. So this means that there are two important properties of this, that for every member of the set, X is always less than equal to M, or we can also take it as supremum as alpha, because already I have taken this notation capital M earlier as a bound. So this implies that X is less than equal to alpha, where alpha is a real number. I mean, among all upper bounds. Obviously, this supremum is also bound because it is least among all upper bounds. So it is again going to be greater than equal to all the members of the set. Second, for every X, for any epsilon greater than 0, for any epsilon greater than 0, there exists at least one member from the set such that X is greater than, say, alpha minus epsilon, where alpha is a real number claimed as supremum. So X is greater than alpha minus epsilon, that is alpha minus, that is alpha in between alpha minus epsilon and alpha, we have always at least one member from the set. This one is important because alpha is the least upper bound. Alpha is the least upper bound. So no member less than alpha, that is no, epsilon is a real number, alpha is a real number. So no member less than alpha is going to be its, upper bound. So for this, there exists at least one member X from the set which is greater than alpha minus epsilon, or there exists at least one member from the set which lies in between alpha minus epsilon and alpha. So the same reason can be used in case of infimum of the set. All the definition will be required in the proof. So next one is that, let me recall what we mean by infimum of the set. Infimum of the given set, say S of R. Suppose infimum of this given set is beta. That is, infimum means greatest lower bound. Greatest lower bound. Greatest lower bound. So we say that infimum of the set S, which is subset of R, is beta if, first, for every X belonging to the set, X is greater than equal to beta, and second, that is for any epsilon greater than 0. For any epsilon greater than 0, there exists at least one member T from the set such that T is less than beta plus epsilon. Beta is again a real number. So that is in between beta and beta plus epsilon. We must have at least one member. See, if this is, say, however, this set may or may not be an interval. So suppose this is the set given to us and all the members here are its lower bound, and among all the lower bounds, suppose this one is the beta. infimum of the set. So according to definition, among all the lower bound, once a set is bounded below, then we can claim of existence of infimum of the set, and that beta must possess the following property. Since beta is also a lower bound, this means that x must be, every member of the set x must be greater than equal to this beta. And second, whenever there is beta minus epsilon, whatever epsilon greater than 0 we choose, there exists at least one member from the set which lies in, we have beta, and whenever we have beta plus epsilon, we have beta plus epsilon here, then this implies that since beta plus epsilon is not a lower bound now for this, because B is the greatest among all lower bounds, so beta plus epsilon will never be its lower bound. This means for discarding that beta plus epsilon is not its lower bound, there exists at least one t belonging to the set such that t lies in between beta and beta plus epsilon. So this one is the definition for infimum of the set. Now using this, why I am recalling this, because all this I will use this in the proof. So after recalling this, the proof seems to be easy. And another definition which I would like to recall is the definition of limit point and statement of Bolzano Weierstrass nested interval lemma, nested interval property. So using this, we will do the proof of this Bolzano Weierstrass theorem. So for that, let me recall the definition of. So okay, I will when discuss the proof using this nested interval lemma, then I will recall the definition of statement of nested interval lemma. But before that, let me recall the definition of limit point once again. Limit point once again. Limit point. So a point, already I have discussed all this in my previous lecture. So a point L belonging to R said to be limit point of a given set is said to be limit point of a subset S of R if every neighborhood of L, say if every neighborhood of L has a point S other than has a point of S of the set S other than L. That is for every epsilon greater than 0, that is every neighborhood of L minus epsilon, L plus epsilon, minus say L, its intersection with the set, or because it, or one can also write in this way that every neighborhood of L intersection S minus singleton L, this should be non-empty. That is, or I can say that in other, that is every neighborhood of L has a point of S other than L. Has a point of the set S other than L. Or the intersection is infinite. Intersection with the set S is infinite. Or every neighborhood of L has infinite members of the set S. So this one is the definition for limit point, and we have seen that all these statements are equivalent. In my earlier lectures already I have proved. Now using this I am going to do the proof of Bolzano Weierstrass theorem. Now let us come back to this statement of Bolzano Weierstrass theorem. So according to Bolzano Weierstrass theorem, every infinite and bounded subset of R has a limit point. Has a limit point means has at least one limit point. Has at least one point, or its derived set is non-empty. So for the first method, which I am going to discuss from the book of N.P. Bali. So for this, what will be the criteria here? Now let us look at what is given to us. It's given that the set is infinite and bounded. So according to statement, we are here the set is infinite and bounded. So in the proof, since the set is infinite and bounded subset of R, so since the set is bounded, this implies there exist real numbers. Using the definition of boundedness, there exist real numbers, say small k and capital K, both are real numbers, such that this k is less than equal to s is less than equal to capital K for every s belonging to for every member of the set. This is the definition of boundedness. Since the set is bounded, so we can always have real numbers, say denoted by small m or capital M or capital K, such that every member of set S lies in between these two real numbers. So now we are going to do the construction. We are going to construct a set T as follows, that T is collection of all those real numbers such that T is greater than finitely many element of the set. T is greater than finitely many elements of the set S. So we are going to collect those real numbers here, which is greater than finitely many elements of the set. So first we will claim that this set is non-empty and bounded above, and then by order completeness property of R, it must have lower bound. So using the this order completeness property, we know that set of real number is an ordered set, and using completeness property of R, every non-empty subset of R, every non-empty and bounded subset of R has supremum as well as infimum, and if it is bounded above, then it will have supremum. So using this, we are going to first claim that this set is non-empty. So for that, what we will do here, that suppose, let me construct here, suppose this one is your real number, this one is the real number, and let because every member of the set is enclosed, every member of the set is enclosed in between small k and capital K. So let me draw here small k, and this one is capital K. This one is a capital K. Now the given set is may or may not be an interval. Remember this set only it's given that every infinite and bounded subset of R. So nowhere it is mentioned that the given set S is an interval. It may be a set like this, say 1 by n, where n belongs to n, which is not an interval. But we will see that it has limit point as 0 using Archimedian property of R. So limit point as 0. So the given set may or may not be an interval, but since the set is bounded, so we can always enclose it in between two real numbers, say small k and capital K. So let me show here. This is the members of the set are enclosed from k to from small k to capital K. Now we will prove in next step, we are going to prove that this set is non-empty, that T is non-empty. Because for using the order completeness property of R, completeness axiom of for real numbers, that every bounded non-empty bounded subset of R has non-empty bounded above subset of R has supremum. So we need to show that T is non-empty. So to prove that T is non-empty, that there exists at least one member in the T, it is very clear from the diagram that from this construction, it is very clear from this construction that k is less than equal to s, small k. Let me write here small k. This is less than equal to s because k is its lower bound. So for every s belonging to the set, clearly because k is its lower bound. So it is going to be either equal to the members of the set or less than the members of the set. So, and we know that, so I can say that k is greater than no element of s. K is greater than no element of the set S. This implies K belongs to T because it is going to fulfill the requirement of this construction T, because T consists of all those members which is greater than finitely many element of S. So since K is greater than no element of S, so this member K will be in side T, and this implies that T is not equal to 5. This implies that T is not equal to 5. That is, T is non-empty. So in the first part of construction, we have seen that the set is non-empty. Now next, to claim this completeness property of real number on the set T, because T is subset of R, we need to also show that it is bounded above. So for that, because T is defined as, let me write again here, because T is defined as collection of all those real numbers such that T is greater than finitely many element of S, finitely many element of the set S, and we have shown that T is non-empty. T is non-empty as this small k will be at least in T. Now to prove that T is bounded above, next aim is to prove that T is bounded above. So for that, what we will do, now just recall the construction. Suppose this is R and the members of the set S are enclosed between small k and capital K. Here the members. Set S is infinite. Remember that set S is infinite. So for this, now look at the construction here. And suppose T is like this. Let me denote T as maybe like this. This one is the T, which is non-empty, and at least k is in the small k is in the T here. So for any epsilon greater than 0, now see, for any epsilon greater than 0, this k plus epsilon is greater than k, because k is a real number. So k plus epsilon is a real number. So k plus epsilon is greater than k, where epsilon is greater than 0. So k plus epsilon is greater than equal to k, and k is the upper bound. This one is the capital K. K is upper bound, so it is going to be greater than equal to the member of the set for every s belonging to the set, for every member of the set. So, and the set contains infinite members. Look here, as per the required we are provided with the set S, which is infinite, and k is greater than equal to every member of the set. K is greater than equal to every member of the set, and the set S contain infinite elements. So obviously k is greater than equal to infinite member of the set S. So this implies that k will not be inside T, because as per our construction, capital T is collection of all those T which is greater than only finitely many element of the set S. So I can say that this implies that k plus epsilon k plus epsilon does not belongs to the set T, and similarly k will also not belongs to set T because it is greater than infinitely many element of the set, in fact every element of the set. So this implies that for every T belonging to T less than capital K, this implies T is bounded above. Clearly this set is bounded above because K as well as K plus epsilon are its bound. T is bounded above. And we know that whenever a set is non-empty, every non-empty subset of R bounded above has its least upper bound. So because we have claimed that the constructed set T is bounded above and is non-empty, so now under completeness property, completeness axiom, one can claim that this set has at least one, say among all this upper bound, I mean k plus epsilon, there exists among all these upper bound, because we have proved that T is bounded above. So from completeness axiom of R, right here, from completeness axiom, whose statement I have written earlier, that every non-empty bound subset of R bounded above has supremum, that is least upper bound. So among all the bounds, the least one is called as supremum. So here we will this implies T is a non-empty bounded above subset of R. T is a non-empty bounded above subset of R. So this implies that T has the least upper bound or supremum. T has the least upper bound or supremum, that is among all upper bound, the least one is called as supremum. Say U. Now what next we need to show that we will show that this U is the required limit point of the set. This U, which is supremum of the constructed set T, is going to be the limit point of the set S. Now recall limit point of the definition of limit point. If it is limit point, if this U is limit point of the set S, then every neighborhood of U, this again U is a real number, so every neighborhood of U must contain infinite member of the set S. So we need to show that within every neighborhood of U there lies infinite member of the set S, or at least one member of the set S other than U. So this is the requirement. So in next part what we are going to do, so next is to prove that U is the limit point of the set. U is a real number, least upper bound is a limit point, but remember that U is limit point of the set T, not S. So to prove that U is a limit point of a set S, U is a of the given set S, which is, so for this what we will do, that again let me draw here. This one is minus infinity, this one is infinity, and this one is small k, and this one is a capital K, in which the members of S are enclosed. Number of S are enclosed, and as per construction we have denoted here some this one is a rough diagram just to have the understanding. We have constructed T, which consists of all those elements T, which is greater than finitely many element of S only. So we have seen that this set K is non-empty because at least a small k will be there, as per the construction. So to prove that U is the limit point of the set S, let us take an arbitrary set of neighborhood of U. So let U minus epsilon u plus epsilon be any neighborhood of u, be any neighborhood of u, neighborhood of the real number u. Since u is the since u belonging to R is the least upper bound or supremum is least upper bound of T of the, this implies for any epsilon greater than 0, for any epsilon greater than 0, see this set T is bound, we have proved that this set T is bounded above, its bound are k plus epsilon, all it's bound. So since the set is bounded above, so there exists it's as per completeness axiom of R, every bounded non-empty bounded subset of R will have its supremum. So suppose supremum lies here, say u, because among all the upper bounds the least one is supremum. So just for the sake of understanding, let me denote here this by u as this u, because among all upper bounds the least one is u, and we will take its uh, neighborhood of u plus epsilon, u minus epsilon. Then what we are going to show here that in between u and u plus epsilon, in between u and u plus epsilon, there lies infinitely many member of the set, infinite element of set S, and here only finite. In fact, we are going to show that every neighborhood of u will contain infinite member of the set S, and hence S is the limit point. So to claim that since u is the least upper bound of T, so whatever epsilon greater than 0 one choose, there exists some, just recall the definition of supremum, there exists some T belonging to T, because this set we have considered as supremum of T. So for any epsilon greater than 0, there exists some T belong to T, capital T, such that T is greater than u minus epsilon. That is T is greater than u minus epsilon. So what will happen that now T belongs to T. Just look at u plus T is greater than u minus epsilon. T is greater than u minus epsilon means that T is greater than finitely many element of S. Finitely many elements of the set S. Why this T is greater than finitely many element of this set S? Because u is the least upper, here it comes from that u is the least upper bound of T, u is in T. So as per construction, capital T is collection of all those elements which is greater than finitely many element of S, and on this, see if this is the this T is greater than u minus epsilon, this means u minus epsilon is left to T, u minus epsilon is left to this small t. So since this T is greater than finitely many element of the set S and u minus epsilon is less than T, so it is again going to be greater than finitely many element of it, and as per construction, this implies that u minus epsilon is greater than finitely many elements of the set S, and hence u minus epsilon, this implies that finitely many element of S lie to the left of u minus epsilon, because u minus epsilon is now a member of the capital T. So this implies that finitely many elements of S lie to the left of u minus epsilon. Remember that phi is also considered as finite. Empty set is also considered as finite. So this implies that infinitely many element of S lie to the right of u minus epsilon. Infinitely, because the set is infinite. Infinitely many element of the set S lie to the right of u minus epsilon. right of say q minus epsilon. Now also what will happen that u is the least upper bound of, we have assumed that u is the least upper bound of t. So let me write here that also this u is, we have considered u as least upper bound of the set t. So this implies that u plus epsilon will not be in t. Why? Why u plus epsilon will not be in t? Because u is considered as the least upper bound. U is considered as the least upper bound of all upper bound. U is the least among all the upper bounds, and u plus epsilon will be for epsilon greater than 0. U plus epsilon will be greater than and right to u, and as per, since u is the one of the bound, see every either this least upper bound, because sorry, supremum is the least among all upper bounds, so but again supremum is also bound for the set, so it is going to be greater than every member, greater than or equal to every member of the set S. So this will, so you will not be in the construction of t, and u plus epsilon is greater than u, so again it is not in t because it is greater than infinitely many member, in fact every member of the set S. So as per construction u plus epsilon will not be in t. So this implies that u plus epsilon is greater than infinitely many element of S. U plus epsilon is greater than infinitely many elements of the set S. So this implies that infinitely many elements of set S lie to the left of u plus epsilon. That is, suppose here we have u, this one is u plus epsilon. So in this one we have, because u plus epsilon is greater than infinitely many element of S, and only finite element of S lies to the left of u. So in this domain we have infinite many element of the set S. So combining this result, that here lies finite members and here we have infinite members, it the requirement that every neighborhood of u will have infinite member from the set is complete now. So this one is the required definition of limit, and since epsilon is greater than 0 is arbitrary, here epsilon greater than 0 is arbitrary, so we can say that this u, which is the least upper bound of the set t, is going to be at least one limit point of the set S. So this is one of the construction, and students need to revise it from the book which I have mentioned here. This is a very good proof, good book. In this, I have taken this proof from this book. So just revise it from NP Bali. I have given the idea how to do it. Now another approach. Now we will see that it's counter example, but let me complete the second proof also. So another proof for the statement of Bolzano Weierstrass for said that the statement was that every infinite and bounded set has limit point. Has at least one limit point. Whenever we say that has limit point means has at least one limit point. Has at least one limit point. So for its proof here, I can say that this one is the second method which I am going to give you an idea for this. So But before this, actually in this proof, in the second method, I'm going to use the nested interval lemma. So let me first recall the statement of nested interval lemma. Already I have used this statement in one of the proof of say incountability axiom when I was doing some proof theorem on countability, that to show that R is uncountable. There I have used this. Let me recall this statement. So if In is equal to say An Bn, where n belongs to n, is a nested sequence of closed and bounded interval. Is a nested sequence of closed and bounded intervals. Then there exists a number, say L belonging to R, a real number, such that L belongs to each of the In for all n belonging to n. But here the important thing is that one is the nesting, and there is the set should be closed and bounded. So and if and apart from this, remember that if the infimum, the length, that is the length of interval, if infimum of this length of interval bn minus, I mean each In, n belonging to n, is 0, then the number L contained in In for all belonging to n is unique. Then L belonging to In, then this L for every n belonging to n is going to be unique. So this is the requirement. One can revise this more about, if one is interested in this nested interval lemma, then one can revise it from the book of Bartley and Sherbert. So definition of limit point already I have recalled. Non-nested interval of lemma property I have. So here what I am going to do, that using the completeness property of R, completeness axiom of R, completeness axiom, nested interval lemma, and the third one is Archimedian property of real numbers. Using these three, I am going to show that every infinite and bounded subset has at least one limit point. Archimedian property of real numbers. So these three I will require. So let us see how this proof works. Now, it's given that the set is bounded. So as per the definition of boundedness, if set is bounded, then it can be enclosed in interval of finite length, because there always exists a small m and capital M or small k and capital K, just for the notational purpose. If S is bounded, then it can be enclosed in interval of finite length. Then, since S is the bounded subset of R, it may not be an interval. Again, I am recalling here, most of here S is, this set is just given that infinite and bounded. So it may or may not be interval. It may be a set like this, say 1 by n, where n belongs to n, which is not an interval. So suppose, since S is bounded subset of R, this implies that for every x belonging to the set, there exists small m and say denoted by capital M, such that the members of X gets enclosed between these two real numbers, or one can denote it by say, or one can take it A or B, or one can also enclose in it supremum and infimum, because we know that among all upper bounds, the least one is the supremum, say B, and the among all the lower bound, the largest one is the greatest one is the infimum, say A. So one can always enclose the set into its supremum and infimum. However, any interval will work here. One can take any upper bound and any lower bound, any upper and any lower bound. So this is going to work here. Now, since the set is bounded, so let me write here that since the given set is bounded, therefore I can say that S can be contained into A and B, and let me call this interval as I0. So the length of the interval, see here the metric is usual, so it will be mod of B minus A, the length of the interval. Yes. So since this one is for the length of interval, this notation I have taken here for the length of interval. So the length of interval will be mod of B minus A. Now since the set is infinite, it's given that the set is infinite. So what we are going to do here is that I'm going to divide this set AB into two equal halves. Say its midpoint as A plus B by 2. Now select that interval which has infinite element. Select that interval which has infinite elements. Now see, union of finite set is finite. So therefore at least one interval must contain infinite element. And if both are infinite, then one can choose, if both parts are contains infinite number, then choose randomly any of them. So what we will do here is that, so let me write it on the new page. So now select that interval which has infinite elements from the set of S. Select that interval which has infinite element. Such that S, the set with this say A1, B1, say one of the part as A1, B1. I mean, we have denoted it by, say here I have taken A and this one is the real number B and this one is the midpoint A plus B by 2. So if this is the required set which contains infinite number of elements of the set S, then in that case, let me rename this one as A1 and this one as B1. So by taking because it contains the infinite members of the set S, so let us denote this by I1. Then again I1 has infinite elements. This implies that I1 has infinite element because we have divided into two equal parts, and this closed interval AB will contains all the member of the set S, and among those two parts we have taken the infinite, the set which contains infinite parts, and if both of them are infinite, then one can randomly select any one of them. So since I1 has infinite elements, as per our construction, infinite elements, so similarly one can again divide this I1 into two equal halves and construct I2. So in that way one can construct IN. The nth, at nth step what will happen, that the length of, one can construct the nth interval I is denoted by IN, and length of the IN, actually either you write here norm of X or mod of X, on R under user metric both are same. So the length of interval IN In is equal at nth step will be b minus a by 2 raised to the power. And again the nth interval in denoted by in has infinite elements of the set S. This in has infinite element of set S of the set S. So actually the purpose here is that we want to apply this nested interval lemma, and for the nested interval lemma we know that that actually what will happen here, we want to create the nesting of intervals, and the nested interval should be closed and bounded. Then only we can claim a real number L which belongs to each of the intervals. So all these we are doing for that purpose. So as per the requirement in nested interval lemma, we have created the nesting of the intervals. Say I naught, I1 is contained into I naught, I2 is contained into I1, and so on. As nested, that is the nested sequence of intervals. Nested sequence of intervals. And one can also see that when n tends to infinity, that is the length of infimum of the length of interval will be 0. That is in will length of the interval will tends to 0. So in will have a single element as per definition of this nested interval. In will have a single element which is common to each of the in. Now suppose that suppose that in that the element common to each of the L is in. I mean L belongs to in for every n as per nested interval lemma. Because all the requirement we have done here, nested interval property. Because in nested interval property we need to have the closed and bounded set, plus nesting of the sets. So we have seen that this closed interval AB, in that we have constructed this A1 B1 by dividing into 2 equal half and this. So here each set is closed, and we know that closed intervals are also closed sets in R under usual metric. So A1 B1 is enclosed into AP. Similarly, A2 B2 will be enclosed in A1 B1. So here we have nesting, and each of the set is bounded. It's already given that the set is S is bounded, and we have closed into AB. So here one can also write it as AB intersection S. There will be no, because AB will contain the member of S. So at each step we can take the intersection. Or this will also going to work. Okay, keep it intersection the set S. Now here what we are going to do, because that is sorry, no need to write here in the set. We have already created the nesting here, and now what we are going to do here, that we will claim that this L is the required limit point. So to claim that L is the required limit point, one must show that every neighborhood of L contain infinite member of the set S, or at least one member other than L. This is the requirement here. So that claim we are going to do by the help of this Archimedean property of real numbers. So now consider neighborhood of L, that is for every delta greater than 0, L minus delta and L plus delta. Now if we are able to show that every neighborhood of L, every delta neighborhood of L is L minus delta, L plus delta, intersection the set S minus L, this set is non-empty, that is then L, because delta is arbitrary, so L is going to be limit point of the set S. So this is our requirement. Now for every, from Archimedean property of R, from. Now we know that each of the in is going to contain infinite element of the set S as per our construction, each of the in. So what we will do that from Archimedean property of real number, from Archimedean property of real numbers, from Archimedean property of real numbers, one can always construct the intervals say IR contained into this neighborhood L minus delta into L plus delta, because each of the IR contains infinite members of the set S, contains infinite member of the set S. So because each of the member here, and if this contains infinite member of the set S, then its superset is also going to contain infinite member of the set S. And since delta is arbitrary, so every neighborhood of L is going to contain infinite member of the set S. So this one is the required logic. Now for every delta greater than 0, one can always construct, or they say at rth step, if this interval say is IR, then for any r greater for any r then for any r, one can always construct the interval of this length using Archimedean property of r for n greater than r. I mean, there exists at least one r such that for n greater than r, one can always do from this Archimedean property of real number. Just look at the previous lecture on Archimedean property of r. This I have explained there. So what will happen that if we try to construct arbitrary neighborhood of L, that is L minus delta, this is L plus delta, then one can always construct this b minus a by 2 to the power n, that is L plus b minus a by 2 to the power n, such that this interval IR, which contains infinite member of S, gets enclosed in this L minus delta to L plus delta. And since this contains infinite element members of the set S, so its superset is again going to contain infinite member of the set S, and L is the limit point. So this type of construction one can always do. This implies L is limit point of this. Limit point of the set S. So just look at what we have used, what things we have used here. We have used the definition of this. Sorry, we have used the property of a nested interval lemma, but for that we have constructed. This is the reason why we have chosen this closed interval AB. We have enclosed the set S into the intervals of this type closed interval, just to apply the nested interval property. And from Archimedean property of R, one can always claim interval IR, which contains infinite member of the element of S and get enclosed in this set, and that is its intersection with every neighborhood of L is non-empty, and this is the reason why it contains infinite member of the set S, and thus L is its limit point of the set S. Now there are some important observations here. Let me recall that. Now see, if so, important thing is that if set is infinite, if S is infinite and bounded, then there exists at least one point, limit point, that is its derived set is non-empty. Now, while remember that the boundedness is not necessary in order for an infinite to have set to have a limit point. It is boundedness of the set is not necessary in order to have infinite set to have limit point. One can construct this. One can take this example. Say half 2, 1 by 3, 3, 1 by 4, 4, and so on. So this set has limit point. This set has limit point as 0. But this set is not bounded. Infinite but not bounded. So an infinite set which is not bounded may have limit point. May have limit point. Now another example is Q, set of rationals. This set is infinite. This set is infinite but not bounded. Infinite but not bounded, still has a limit point as a whole R. The derived set, I mean whole R. Bounded, still has a limit point. Still has limit point. Still limit, that is derived set of Q dash is equal to whole R. So every real number is limit point of Q. But there are sets, for example, set of integers, set of natural number, which we have seen has no limit point. Has no limit point. So for existence of limit point, if the set is infinite and bounded, then there is guarantee of existence of at least one limit point. But if the set is not bounded, only infinite, then it may or may not have limit point. We have seen various examples. Now, other properties related to Bolzano Weierstrass's property, we will look at later on in the next one. So just revise it from the book of N.P. Bali, and we will discuss more in about limit point in the next lecture.